Okay, bienvenidos a lesson 6. So we're going to talk about measuring bivariate data. So when we have two quantitative variables and we want to talk about how strong the relationship is, we have a measurement for the strength that we use, and it's called correlation. So here we're going to define the correlation coefficient. So we use a lowercase r typically. You might see an uppercase r for some folks. I usually will use a lowercase r. And it measures the strength of a linear relationship between two quantitative variables. It's really important to note it only measures the strength between the linear relationship. So if you have a curved relationship, you will not want to use this. Absolutely, the correlation coefficient is highly influenced by outliers. And as far as the correlation coefficient is concerned, it doesn't matter which variable you label the explanatory and which you label the response. Although later on it's going to be extremely useful to have the correct one labeled. So the x values should be your explanatory, the y value should be your response. So to our example for the high school GPA and the first year college GPA, the correlation coefficient here, they fit a line to it. They found that it was 0.82, which we're going to talk about what that means, but it's fairly high. It's a fairly strong relationship. Okay, now for measuring correlation. So the values range anywhere from -1 to +1. Usually they're not going to be exactly equal to -1 or exactly equal to +1. It can happen. It's pretty rare. Usually it falls somewhere in between. So it's always between -1 and +1. So if I have a negative correlation coefficient, it means that when we're talking about form, it has a negative relationship or negative association. And if I have a positive correlation coefficient, it means that if I were to fit a line, it has a positive slope. So I have a positive association. So in general, the closer to -1 or the closer to +1 it is, the stronger the relationship is. The closer to 0 it is, the weaker the relationship. A correlation coefficient of 0 tends to mean that there's no detectable linear relationship between two variables. So here's a good example. I like to have these just on record. So correlation coefficient is equal to 0. It could be if you have a flat line, there's a no slope. The slope is equal to 0. But yeah, there's no line here that's going to really help me with this relationship here. Not too much. Correlation in -0.3 means that, hey, when I fit a line, it has a negative slope, but it's pretty weak. 0.3, it's not that strong. 0.5, it's kind of a moderate relationship. You could argue moderately weak or moderately. It's not too strong, though. -0.7 has a negative relationship here, and the points are closer than when they were at 0.5. Positive 0.9, the points are closer. It's a stronger relationship. -0.99, the points all fit really, really tightly. So it's not just the sign will tell you the direction of the line, and then this value will tell you, well, how tightly are the points fitting the line. So here's an example. Determine which value is the best estimate. So knowing nothing about actual calculating here, what is our best estimate? And I'll give you a second here. Okay. As before, one thing that I was a big fan of doing is reducing the number of answer options. So right off the bat, you cannot have a correlation coefficient less than -1. It cannot be this. Then I'm going to look at a correlation coefficient of -1 means that the points all perfectly fit a line. and that line has a negative slope. I would argue that there's no line that you can draw where they all fit. So I would say not negative 1. Positive 0.95, this means that there's a really strong positive trend, but there's no line I can fit where nearly all the points fit. So I would argue not this. So now I have 2 options here. So things to consider, positive 0.584 means I have a moderately strong positive relationship. Looking here, I don't feel like it's that strong. It's kind of hard to tell. I would argue it's probably maybe something like that, maybe a slight negative slope. It's actually going to be negative 0.08. Probably slightly more. So here's another example, another scatter plot. So using what we know, figure out which is our best estimate for the correlation coefficient. Okay, so once again, I'm going to go ahead and reduce the number of answer options. Negative 1 and positive 1 are both scenarios where all of the points would perfectly fit a line. Looking here, I would argue that can't be true. There is no line I can fit where all of the points would fit on that line. So it's not going to be A or F. And then I could look at B and E next. A correlation coefficient of negative 0.9 or 0.90 or positive 0.95, that would be a really, really strong relationship where all of the points, or most of the points, fit pretty close to a line. I would argue no, probably not. I would be able to deduce these out. And for me, if I wanted to fit a line, of course, I'm eyeballing it. There is an official way how to do this. I would argue there's probably a positive relationship, especially because of this point right here. If it weren't for that point, it would be harder to tell. So based on that, it's positive. I would go with here. It is a moderately strong relationship. The points are all relatively close to a line. Okay, here's another one. So we have this scatter plot. We want to estimate best guess for the correlation coefficient. Okay, so we have seen this one before. If you remember, we argued that this was a nice curve, right? We wouldn't want to fit a line to it. If this is a curve, you can jump straight to, we shouldn't be using the correlation coefficient because it's not linear. Some people would still fit a line to it. This is actually a fairly strong positive relationship, but it really ought to have a curve fit to it, not a line. And I think this is the last one in this set here. So determine best guess correlation coefficient. Okay, so I like to do this a lot. I fit a line to it. There's kind of an oddball point there, but I would argue it's linear. So I would say, no, it's not going to be E. But based on what I just drew, when I go from left to right, I'm going downward. So this is a negative relationship. That means I need to focus on the 2 negatives. So negative 0.87, that's a fairly strong relationship. Negative 0.10, that's pretty weak. That means that we're going to have a hard time seeing this trend. It's not very strong. I would argue this is a clear linear trend for me. So it's negative 0.87 is going to be the closest bet here. So we do want to caution you about correlation. It is an incredibly useful thing to use. However, you need to be cautious about when you use it. You must only use it when both variables are quantitative. You never want to use it if you have a categorical variable. And it does not describe curved relationships. So if you have a really strong or whatever curved relationship, you do not want to use correlation coefficient. It's not resistant to outliers, so that means that you can have a really, really strong relationship and an outlier, and that outlier will mess up your correlation coefficient. And it's not a complete summary of your two variable data. Always plot. Might autofill a bit. So always plot your data. Always look at it. It's super important to know. So this is what I mean, it's not enough. All four of these graphs have the same correlation coefficient of 0.7. But 0.7 alone doesn't universally describe these. So if you look here, I have a big old cluster and I have an outlier. If I didn't have that outlier, I would not argue this has a correlation coefficient of 0.7. I would not argue that at all. Here, we have an outlier here. But honestly, if you didn't have that outlier, that correlation coefficient would be a lot higher. So in the third, I see two big old clusters. You probably would want to actually look at those clusters individually. There's usually something going on there. Here, this is the only one that actually kind of makes me happy. I don't have major outliers or clusters. I would trust this correlation coefficient of 0.7 more than I would for the others. But yeah, this is just to show you correlation coefficient by itself is not enough. You also need to be looking at the graph just to see what it looks like. So we're going to talk about correlation versus causation. You've probably heard that the hokey like correlation does not equal causation, and it really, really doesn't. So just because two variables have a very strong relationship does not mean that one of the variables is causing the changes in the other. You don't want to jump to that conclusion. So a possibility here is you might have a lurking variable. So a lurking variable has an association with the other two variables. So you might have an explanatory and a response variable, but maybe there's a lurking variable that's affecting both of them that you didn't account for. It lurks, right? So for example, there was a study recently, they showed there was a strong correlation between countries that have more TV sets per capita, so like more TV sets per person in that country, and longer life expectancy. So we want to caution you, you don't want to jump to the conclusion, oh my gosh, having more TVs causes people to live longer. Probably not. So think for a second, what is a possible lurking variable here? I would argue economic prosperity. So in general, if a country has more money, more people tend to have more TV sets, and they're more likely, not guaranteed, but they're more likely to have access to health care if they have a better economic prosperity in that country. So that's definitely a variable that could, economic prosperity can affect how many TVs per capita there are in a country, and it can affect longevity just because people can get access to health care. I threw in a few examples here. I like these. These are actual headlines to articles I found. Someone shared with me, like, oh my gosh, I love my horse so much. Studies show that women who own horses live 15 years longer than those who don't. Does this mean that I should rush out and buy a horse so I'll live longer? Chances are this has more to do with, once again, economic prosperity. Folks that own horses are more likely to have access to health care. You tend not to own a horse if you're very poor. Not in this country anyway. Do ice cream sales increase shark attacks? Because it's been shown that as ice cream sales go up, so do shark attacks. However, I wouldn't jump to this conclusion either. And this was kind of a mock article. The idea is there was a lurking variable of weather, like sunniness. Is it very sunny? Is it very warm? Because when it's sunny and warm, ice cream sales go up. And when it's sunny and warm, much more people go to the beach, which increases the chances of a shark attack. I would also argue it doesn't go the other way. Shark attacks increasing don't cause ice cream sales to increase. I thought this one was a fun one. There's a whole website dedicated to odd relationships here. But this one, it's asking, hey, does Nicolas Cage cause swimming pool drownings? The background behind this is that the number of roles that Nicolas Cage, so he's an American actor, gets in movies in a given year are very related to the number of deaths by falling into a swimming pool in the US. However, we probably don't want to jump to the conclusion that Nicolas Cage getting more roles in movies is causing these people to drown. That is very, very unlikely. So yeah, that's going to make it for this lesson. We'll see you for lesson 7.